Welcome to our classroom. Welcome to the classroom. Welcome to the classroom. The segments where I bring the classroom out into the field.
Welcome to the classroom. Today we're going to build a 3-point problem to try to help you understand the geometry and how the 3 points can tell us the orientation of a plane in space. So I'm going to construct our ground here now, and we'll get into the 3-point problem once we have the topography created. These patches are the geological layer that we want to create. So we would pass along this surface as a complete layer, and then through processes of deposition, we would cover it up, and then through processes of erosion, we'd create our geometry of the current topography. So we have 3 points, 1, 2, and 3. They all lie on the same plane in space. However, we don't know what orientation that plane is, the strike and the dip that describes that plane. So we need to do some calculations. The first step is to connect 2 of the points together, and we know the horizontal distance in space between those 2 points. All right, we need to determine the length of this line, and we know that the plane exists on that line at some angle, and we can calculate the angle from the horizontal, the blue line, down to the plane. Okay. In order to do that, we know the horizontal distance along the map. We can scale it using our ruler, and then we can calculate that length from the scale, and we know the depth difference, the topographic elevation difference between this point and that point. So in our example, this is 600 meters elevation. The ground is at 600 meters, and here we're at 200 meters. And so we have a change in height, okay, of 400 meters down, and the horizontal distance across here. All right, so we have a triangle like this in space, with my thumb pointing at this point and my finger here at that point. And the blue line is the horizontal distance. Okay, so we can calculate that angle. Now that is not the true dip. That's what we call an apparent dip, because we don't know at this point the strike orientation of this plane in space. So we need to determine that. But first we calculate this apparent dip angle, okay, of this triangle here. It's about 14 degrees.
So now we need to go along that blue line. We want to find out where that third point, where the elevation of this point exists on this line. So this line goes from 600 elevation to 200 elevation. It's going to be underground somewhere over here, but we can figure that out. So how we do that is we need to find out where that third point, in our case the 300 meter elevation, would lie, ignoring the ground elevations, where it would lie in space. So we take the difference in the elevation, so it's 3, if we work at the bottom side, so we work from here to here, it's 100 meters drop. We're following the same apparent dip that we calculated because we're staying on that blue line. So now we need to figure out the horizontal distance on our map. So again, tan the angle, opposite over adjacent, work that out, and we get 401 meters. Now remember, we worked from that lower elevation point, so it's 401 meters from this point up along the blue line to a point that exists at the same elevation as our observation point here. All right, it's almost on the contour line over here, but it's not exactly. Therefore, the true dip is somewhere greater than the apparent dip. So now we've got structure contour. That's that green line. We can connect the 2 points we know are at the same elevation. And therefore, we know, okay, high, low, the strike must be in this direction because we've got our high ground over here, our low ground over here. So our bed is dipping down. If we take a cross section, through our blue line there, we know our dip is in this direction, but we don't know how much the true dip is. All right, we calculated the apparent dip, which is along this line. All right, so we've got an offset in terms of the true dip. So now we have to figure out what that true dip is. We need to extend this structure contour line.
Now that we have this line in space, which represents our strike orientation, we need to figure out the true dip. And in order to do that, we need to determine the perpendicular distance from this green line, our first structure contour line, or the strike line, down to one of our other points in space. So we could do it up to that one or this one. This one's closer. And in the example, I use purple line, so we can calculate that perpendicular distance.
90 degrees from our structure contour line and intersects in a known point. And so we can measure that mapped distance, which is about 240 meters in this example. Then we've got horizontal distance. We don't know the true dip, but we do know the elevation change, right? So 240 meters horizontally on the map. We go down 100 meters, so we can work out then the true dip. Now, the true dip is always larger than the apparent dip, so that's something to keep in mind. So now the next step is to figure out, well, where all these structure contours should exist.
So we can actually repeat that with multiple green lines. So we're going to have parallel green lines equally spaced horizontally the same length as this purple line. So that would be here, along there, another one there, another one like that. So each of these then represent the elevation of the plane in space, and they're slowly going uphill there. So what we do, we want to construct these structure contour lines at the same elevation spacing as the topography. So in our example, the topography lines go up by 100 meters, so we can go up by 100 meters as well. So this would be 200, 300, 400, 500, and 600.
So now we need to figure out that horizontal distance from this structure contour to the next structure contour. So we can use this triangle here again to work that out. We can draw on all of our structure contours parallel to that first one. Then we can find the intersection points. We've got dots here in yellow. Those are where the structure contour and the topography are the same elevation. So here we've got 600, 600. All right, we'll go down to the 500 meter structure contour. We just scan along, up 500 dot, 500 dot. Along the 400 meter line, we have no intersection point of the structure contour and the topography at 400. 400's here, 400's over here. 300, walk along, 300's there, 300's there in terms of ground elevation. Structure contour 200, intersects the ground there, intersects the ground there. And now we've got our outcrop pattern. And so we know that we can use the law of V's, but we know that it doesn't exist in the valley here. So we have to think about a couple of options on how we can project, the contact across the entire map area. Remember, we've got this valley in between the two hills. So our surface actually exists in the air. It's been eroded out. We've got a river there, eroded out the ground underneath our contact. So we're going to have outcrop pattern over here, and we're going to have some over here as well. We can safely say that exists here and exists there. There's no point on the structure contour that at 400 that intersects the topography at 400 along this line. So we can't, in fact, make a connection across there.